We are starting Chapter 8 for AP Statistics about confidence intervals, starting off with 8.1 where we are learning about the basics of confidence intervals and what they are. So first we're going to be looking at, in this section, all of these things. Interpreting confidence intervals, point estimate and margin of error, describing how sample size and confidence levels affect the length of a confidence interval, and then talking about practical uses of confidence intervals. Okay, so this is kind of in theory. Let's say that we're trying to estimate some sort of mean. We know the standard deviation, we know what our sample size is. We have sample size of 16, standard deviation of 20, but we don't know what our mean is. So there is a way that we could have that stored on a calculator and just find the mean of a whole bunch of samples of the same size with the same standard deviation to estimate what that mean is. And here we have a mean of 240.79. So what we're going to try to do is figure out, using confidence intervals in this section, how can I figure out a more precise estimate or a range of estimates for what this mystery mean is. So if we had to give one number to estimate an unknown population parameter, what would it be? If you were estimating for the mean, then you would use the sample mean x bar. If you were estimating for population proportion p, then you might use p hat. In both cases, what those are called are point estimates. You are providing a point estimate of the parameter of interest. So basically, you're just using the sample instead of the parameter. A point estimator is a statistic that provides an estimate of a population parameter. The value of that statistic from a sample is called the point estimate. In Chapter 7, we learned that an ideal point estimator would have no bias and low variability. Since variability is almost always present when calculating statistics from different samples, we must extend our thinking about estimating parameters to include an acknowledgement that repeated sampling could yield different results, which is why we end up with a interval of estimates. So here we have an example where we're looking at we need to determine the point estimator and then calculate the point estimate. Quality control inspectors want to estimate the mean lifetime mu of the AA batteries produced in an hour at the factory. They select a random sample of 50 batteries during each hour of production and then drain them under conditions that mimic normal use. Here are the lifetimes of the batteries from one such sample. So we need to talk about what would the point estimator be. So remember, that's where we're going to either use x bar if we're trying to find mu, or p hat if we're trying to find p. In this case, since it's talking about, let's see where it says in the question, mean lifetime mu, our point estimator then would have to be x bar, and our point estimate is going to be the actual value of x bar of our sample here. So we have to actually calculate that. In this case, in order to estimate x bar, what I did here was I put all of our values from the sample into our calculator, into the stat list 1, and then I can go back to the stat calc 1 variable statistics. I want to use my list 1 and calculate. It'll give me x bar 16.7176. That would be my point estimate. Okay, what proportion of P of U.S. high school students smoke? The 2011 Youth Risk Behavioral Survey questioned a random sample of 15,425 students in grades 9 to 12. 2,792 of these said they had smoked cigarettes at least one day in the past month. So the point estimator, since we're trying to find P, is going to be P hat. That's the sample proportion. And then our point estimate we have to calculate p hat, which is the number who said they smoke, 2,792, divided by the total surveyed, which comes out to about 0.181 for our p hat point estimate. Okay, if we're looking at the variability of the battery lifetimes that we did in Part A, we put all that data into our calculators. If we want to estimate the population variance, so our point estimator, since we're trying to find population variance, would be our sample variance, which is S squared. And then our point estimate, we'd have to calculate S squared. But we should, off of our calculator, already have S. So that's the 0.664 that we see there. So we would just square that, 0.664 squared, about 0.441 if we round to 3 decimal places. That would be ours squared. Okay, so now we're looking back at this mystery mean activity. We had the example of 240.79. We could guess that it's probably somewhere around there, but we don't know how close it would be. So to answer this question, we ask another question. How would a sample mean X bar vary if we took a lot of simple random samples of size 16 from the population? So here we're trying to find mu, the population mean. If we know the population standard deviation is 20, we took a sample size of 16 and got 240.79. What if we did that a whole bunch of times and figured out how far away they are? So what we're going to do is now take a sampling distribution of X bar. So our standard deviation now, so before it was 20, since we're taking samples of 16, then our standard deviation is now going to be 5, which means our sampling distribution is more normal, more condensed towards that center. And we have all these different, we know we would have variability. So we have all these different X bar examples from each size 16. So we can use the 240.79 as our point estimate. We don't expect mu to be exactly X bar, so we have to think about how accurate we are. So here's a few things that we know. In repeated sampling, the values of X bar follow a normal distribution with mean and standard deviation of 5, which is what we just saw on the last slide. So the X bar distribution is normal. Standard deviation is 5 because of our sample size 20. Remember, we would divide by the square root of the sample size. If we look at the 68, 95, 99.7 rule, we know that 95% of all samples of size 16 would be within 2 standard deviations, since we are saying that it's normal. So 2 standard deviations is 10. Of our mystery mean. So if X bar is within 10 points of mu, then it follows that mu would be within 10 points of X bar. And what that means is that if we know X bar and we know the margin of error is 10, then we can capture 95% of our mu's within 10. So we would take our x bar, which was the 240.79, and we're going to add and subtract that 2 standard deviation margin of error to get an estimate for a range of where mu could be of 230.79 to 250.79. We'd be calculating an interval using a method that captures the true mean in about 95% of possible samples of this size. We know it's 95% because that was 2 standard deviations away. So what we're going to be doing is taking whatever the point estimate is, and we're going to be adding and subtracting some margin of error. That margin of error is going to depend on a lot of things. A C% confidence interval gives an interval of plausible values for a parameter. The interval is calculated from taking the point estimate and adding and subtracting that margin of error, which is the same thing I wrote up there in red. The difference between the point estimate and the true parameter value will be less than the margin of error in C% of all samples. So that in our last case, that was 95% of all samples. The confidence level C gives the overall success rate of the method for calculating the confidence interval. So in C% of all possible samples, the method would yield an interval that captures the true parameter value. So going back to our mystery mean, the confidence level is the overall capture rate if the method is used many times. The sample mean will vary from sample to sample, so that's where we have those 3 different values written there. But when we use the method estimate plus or minus margin of error to get an interval based on the sample, C% of these intervals capture the true unknown population mean. So what I'm looking at here on the right side is our true mean in the middle, mu, different values of x bar. Obviously that's going to vary by our sample size, or by each of our samples of size 16, they're all the same size. And we see that the same width intervals, but we notice that they kind of bounce around a little bit. Those orange dots in the middle are going to be your point estimate. Those are all x bars in this case. And we notice that one of our confidence intervals does not cross this mu. All of the other ones do. One of them does not, and we would expect that because only 95% would likely capture mu. So that one blue one down there misses, and all of the green ones do end up capturing mu in the interval. So we're going to be interpreting confidence levels and intervals, and those look very different, and both of those are extremely important that you know the wording. So this is an important page. I would recommend memorizing these wordings. Okay, so I'm just going to write the interpretation here to interpret a confidence interval. We are C% confident. That's obviously going to vary by question what the confidence percent is. That the interval from blank to blank, we're going to have numbers there obviously, captures the actual value of the, and this is population parameter in context. Again, varies by question, but as long as we have the, we are 95% confident that the interval from blank to blank captures the actual value of, and then whatever the context of your question is. We were talking about battery life before. That would be in there as in context. And then if we were interpreting the level as opposed to the interval itself, we would say if we take many samples of the same size, from the population, about 95% of them, or we'll put C% of them because it could vary, will result in an interval that captures the actual, and again, this is just parameter value, which we'll have in context. We'll put that in brackets again to indicate we need to put that in context. So those two statements are statements you need to become familiar with, and it depends on whether you're interpreting the actual interval itself or just the confidence level as to which one you would use. The confidence level tells us how likely it is that the method we are using is going to produce an interval that captures a population parameter if we use it many times. The confidence level does not tell us the chance that a particular confidence interval captures the population parameter. So we're not going to say I'm 95% confident, like I'm not going to say that I have a 95% chance of capturing the population parameter. You cannot say it that way. You have to say that if I do this many times, 95% of them, or however many percent of them, will capture the mean. So we're not going to state this in terms of probability. We interpret confidence levels and intervals in much of the same way, whether we are interpreting mean, proportion, or some other parameter. Again, it's kind of like those two statements are what you're going to need to know. You just plug in whatever you don't. Okay. The Pew Internet and American Life Project asked a random sample of 2,253 U.S. adults, do you ever use Twitter or another service to share updates about yourself and see updates about others? In the sample, 19% said yes. According to Pew, the 95% confidence interval is between 0.167 and 0.213. Interpret both the interval and the confidence level. So remember, with the interval, we always start with, and we always use the royal we here. We are whatever percent, in this case 95% confident that the interval from, and here we use the numbers they gave us, 0.167 to 0.213 captures the true in this case we're talking about a proportion of all adults. I guess it's US adults who use Twitter or another service for updates. So yes, these do become lengthy, but we do have to make sure that we use context to make sure we use the correct form. So now here we're talking about just strictly the level. So that means we do not use the interval this time. We just use the sample size because remember we have to talk about doing the same thing multiple times. So we're going to say if we take many samples of, in this case, 2,223, US adults were taken, the resulting confidence intervals would capture the true proportion of all US adults who use Twitter another service. And this is where we use the percent, and that would be 95% of the time, or in about 95% of the samples. Okay. Okay, so this is the same kind of deal. This time we're talking about fat content in hot dogs. To find out, researchers measure the fat content of a random sample of 10 brand X hot dogs. A 95% confidence interval for the population standard deviation is given from 0.2585 to 7.55. So this time I'm not going to write unless you want me to, so I will read it slowly. I'll repeat it twice. That way you can write it down if you want to. Otherwise, in the comments of the video, go ahead and tell me that you want me to, and I will add it. So interpret the confidence interval. So this is where we talk about the numbers in the interval themselves. We'd say that we are 95% confident that the interval from 0.285 to 7.55 grams captures the population standard deviation of fat content of brand X hot dogs. So we had to make sure that we understood what we were measuring. Here it says population standard deviation sigma. So we are trying to find the standard deviation. I'm going to say that one more time in case you missed it the first time or want to hear it again. We are 95% confident that the interval from 2.85 to 7.55 grams captures the population standard deviation of the fat content of brand X hot dogs. Now to interpret the level. So we have a 95% level. We don't know, oh, we do have 10 brand X hot dogs. So instead of using 10 like last time we used the actual sample size in our answer, you can say, if this sampling procedure were repeated many times, about 95% of the confidence intervals would capture the population standard deviation of the fat content of brand X hot dogs. I'll say that one more time. So we didn't have to actually say the 10 in our explanation if we don't want to, but you can. You could say if many samples of 10 hot dogs were taken. But I said, if this sampling procedure were repeated many times, about 95% of the confidence intervals would capture the population standard deviation of the fat content of brand X hot dogs. Now let's look to the true-false question. The interval from 2.84, that was a 5, wasn't it? It was a 5. To 7.55 has a 95% chance of containing the actual population standard deviation. So we do not ever give our explanations in terms of chances, so this is definitely false, or probability. This kind of seems like a probability explanation. So there's not a chance of it being in there. It's either in there or it's not. We just talk about the 95% being how many, if we did this a whole bunch of times, how many would catch it. So definitely false. In explanation, I'm just going to say that it either contains sigma or it doesn't. And the 95% is the number of intervals that would capture sigma. If repeated many times. Sorry, my handwriting kind of goes as I keep writing. Okay. So why do we always do 95%? The price we pay for greater confidence, so if we went up to 97, 99, things like that, we're going to have a wider interval, wider margin of error. Because we were 2 standard deviations away, that's why we had the 10 when we did this example. If we were going to use a larger margin of error or a larger confidence, then it would be more standard deviations away from the mean. So that the number of standard deviations away from the mean, that is what we call this critical value. So the critical value is how far away from the mean we are in terms of standard deviations, and then we multiply that by the standard deviation of the statistic. So let's get into that, that form and talk about it more specifically. So again, we have the statistic out front, which varies depending on the example. And here's our margin of error, which is a critical value times the standard deviation of the statistic. Where the statistic is the point estimator. So here's a few properties about confidence intervals. We keep referring to this margin of error. If it just asks me to find the margin of error, it's the everything after the plus or minus. So it's the critical, I'm going to shorten this a little bit, crit value times the standard deviation. So whatever is being added and subtracted, that is the critical value, whatever number comes here. Or I'm sorry, that's the margin of error. Okay, so a couple other properties. The user chooses the confidence level. And that's obviously going to affect, I'm just going to do MOE for margin of error, follows from this choice. The higher your confidence, the bigger your margin of error. Okay. So the critical value depends on that confidence level. So I did mention this, the greater the confidence, then you're going to have a larger critical value. And the standard deviation of the statistic depends on the sample size. Here are two important cautions when you're constructing a confidence interval or interpreting a confidence interval. Our method of calculation assumes that data comes from a simple random sample. And N is from the population of interest. If that's not true, then all bets are off, right? Like you can't do a confidence interval if those things are not true. So if for some reason we know that those things are not true, then we can't be doing a confidence interval. The margin of error covers only chance variation due to random sampling or random assignment. It's not going to cover bad sampling procedures. like under coverage or convenience sampling, things like that. You're not able to just change your margin of error to adjust to those things, because you shouldn't be doing a confidence interval in the first place if you don't have a simple random sample with random sampling or random assignment. And that is the basics. So that's what we covered, and here is the homework for section 8.1.